Hey YouTube, this is my first video in our unit on polynomial functions, in which we're going to define what polynomial functions are, and we're also going to talk about how we could evaluate polynomial functions for given input values, get an output value out of it. So let's go ahead and start by defining what we mean by a polynomial function. We say that we want to recall, first of all, that a monomial is a number, or it could be a variable, or it could be the product of a number and one or more variables with whole number exponents. But we say a monomial is just something like this, like if I said 2x squared. This is what we refer to as a monomial. And the reason why is just because, it just has one term now. Remember also that terms are separated by pluses, okay? Separated by plus symbols, okay? And I say if it's negative, subtraction, you could change it to adding the opposite, but we say terms are separated by pluses and minuses. We say that a polynomial is a monomial or a sum of monomials. So a polynomial function is a function of this form here, where we're adding together several different monomial terms. And so poly, meaning many, is just the sum of some monomial terms. That being said, looking at this right here, we say that truly this is the polynomial function in standard form. So we say f of x equals, or y equals, this a subscript n times x to the power n plus a subscript n minus 1 times x to the power n minus 1, and then all the terms in between all the way down to a subscript 1. This would technically be x to the 1, and then a subscript 0. And we don't need to write x to the 0 here, but this would be our polynomial function. So a few things of note here. We say a subscript n. This is this first number right here, this first coefficient. We say it isn't 0. If it were 0, that term wouldn't exist in the first place. And we say the exponents are all whole numbers. So this is worth underlining here. All of your exponents, I'll have you know you can have a decimal exponent. We're not going to deal with those at this point in time, but for a polynomial function, all of these exponents are going to be whole numbers, and the coefficients are all real numbers, so no imaginary coefficients, okay? If this is true about all of these monomial terms that we're adding together, then we say that it is a polynomial function. So a few items of note here before we kind of talk about standard form of a polynomial function. We say for this function, a subscript n is the leading coefficient. Now, leading coefficient, what I'm going to tell you is, as you look at all these polynomial functions down here, I hope you see this right now, all of the exponents are going in decreasing order. We're going to call this standard form. But when you have it in standard form and all the exponents are in decreasing order, the term, or the monomial term that has the highest exponents, in the front. And so we say that that front coefficient gets a special name. It is called the leading coefficient. I'm going to write capital L, capital C. I'm going to draw an arrow here, and I'm going to label this. That is our leading coefficient right there if it's written in standard form. Now we say n. N is the degree, and I'll point out n here. N is this highest exponent. When you have it in standard form, it is the highest exponent. So we say the degree of the entire polynomial. Every term has its own degree. This term over here is second degree, but the highest exponent is the degree of the polynomial. It's really important we can identify that. And then a sub 0, we say this is the constant term, this thing over here that they've written in green. We say that this is the constant term, and this is something we often pay attention to because, well, first of all, it's the only term that doesn't have a variable on it. And it also has graphical implications as well. But we'd say that if polynomial function is in standard form when its terms are written in descending order of exponents from left to right. So we always put the highest degree term in the front. That'll tell us the degree and the leading coefficient, and then the constant should always be in the back if you have a constant term. So common polynomial functions, well, I'll point a few things out to you here. For any functions that have degree 0, degree 1, or degree 2, we've already seen in the past. These are constant functions, these are linear, and these are also parabolic or quadratic functions. So these, as an example, would be, y equals negative 14. We could also write this as y equals negative 14. But this would be a polynomial function with technically degree 0. Remember, anything to the 0 power is 1. So this is really saying the same thing as negative 14 times 1. But we don't write the x to the 0. We just assume that this is a 0th degree thing. We have a first degree thing here. You notice that the 5x to the first comes before the constant 7. And then our second degree thing here, this standard form of a parabola, really is a polynomial. And we say that we have 2x squared plus x to the first minus 9. Now these other two down here, the cubic and the quartic, we want to know these names. Cubic because we have the highest term being cubed. And then we say the quartic, well, because the highest term is being taken to the 4th power, we can associate that with the word quartic. So we would say that going in standard form here, you see how the exponents are going in decreasing order. And even this right here, f of x equals x to the 4th plus 2x to the 1st minus 1. We didn't even have an x to the third or an x to the second term, but we can still say that with this in front, our leading coefficient is 1 and our degree is 4 on this. So now, looking at polynomial functions and having defined them, what I want to do here is decide whether the function is a polynomial function, and if it is, we're going to write it in standard form, identify its degree, type, and leading coefficient, which are all pretty easy things to identify. So this first function here, I'll tell you, I recognize is a polynomial function. And the reason why I know this is because all of the exponents are whole numbers. Look at this. They're all whole numbers, and all of the coefficients here, all of them are real numbers. So we're going to rewrite this in standard form, which means that our x to the second term needs to go first. So I have 1.6, I'll try to squeeze that in there, negative 1.6 x to the second, and then would come next our negative 5x, and then last our positive 7. So we have 3 terms in this trinomial, and we would say that, well, what do we want to recognize here? It's degree. Degree of this polynomial would be the highest exponent on any monomial term, and it'll be the one in front once you get it into this form. So we'll say it's second degree, and the thing we want to do now is label this. This means that it is a quadratic thing. Anything second degree is a quadratic polynomial. Also, we say, what's its leading coefficient? Well, we're just going to write LC. You know, it's kind of a shortcut here, but we'd say the leading coefficient is actually this negative 1.6. If we had looked up here and made the mistake of not putting this in standard form, we might have thought that this was the leading coefficient, but it's really the negative 1.6, or the thing attached to the highest exponent, the variable with the highest exponent. So looking at this next one here, we say, is it a polynomial? Well, I'll tell you right now, it is not a polynomial. And a couple things here. We'd say when you have a negative exponent, we say x to the negative 2 is the same thing as 1 over x to the positive 2. And so this would not be a polynomial. If I rewrote this, it would be x plus 2 over x squared plus 9.5. So it doesn't look like what a polynomial looks like because of this term here. And also because we say that all the exponents have to be positive whole numbers. This is not positive, it's negative, okay? All the coefficients, though, were real, which was a bonus, but we'd say not a polynomial. And then our last one over here, take a look at it. We say, what do we think about this one? Well, all of the exponents are positive real numbers, and whole numbers, pardon me, positive whole numbers. We say all the coefficients are real, 1, negative 6, and 3. So let's put this in standard form. We have q of x then, or y, is equal to, I guess our x to the fourth term would need to be first, and then our x to the third term, and then our x to the first term here. We don't have to write x to the first on that. So things we want to identify here. What is the degree of this polynomial? Well, I recognize that it's a fourth degree polynomial, so its type would then make it a quartic polynomial. And then its leading coefficient, also very important to know this, is this front 3 here. So we say just positive 3. So here's the deal. We're going to be able to recognize these very easily in standard form, but we need to recognize it so that we can graph things. So along the lines of graphing, since we're going to be graphing so many of these, it's going to be important, and modeling real life situations, but it's going to be important that we can find points on the graph. So to find points, you know, for a function like this here, this fourth degree polynomial here, we say if f of x is equal to this rule, what is our y value then when x equals 4? So what we're going to do first is we're going to make a small little table here. We're going to say that this is x and y. And what we're going to do is we're going to plug in a 4 here, and we're going to get f of 4, which means we need to go and find what the value of f of 4 is. So we're just going to use here what we've used in the past, but this has a name. We're going to refer to this as direct substitution. And direct substitution means that everywhere I see an x, I'm going to put this in for my input. So 4, 4, 4. In this case, order of operations we'll need to follow. We say 4 to the 4th. That's like 16 times 16 is 256. That's really fun. We say 4 to the 3rd power is 64. So I have 6 times 64 minus, I can do this one, 12 plus 11 here. So let's double this here. We say negative 512 plus, now this would be 360 plus another, I suppose, 24, 384 minus 12 plus 11. And now, yes, I am going to get my calculator out here. Let's see. Let's do this one. Negative 512 plus a positive 384. We'll start with that there. It's definitely going to be negative. Here we go. So we have 512 negative plus 384 is this minus 12 is this plus 11. And so we get negative 129 if I've not hit any buttons incorrectly here. But we'd say that evaluating this, basically we could rewrite this table and say that this is really 4 comma negative 129. So one important question here is, what is the significance of this point? 4 and then f of 4. And really what we could say is that the significance of this point is it's really 4 and then the y value at x equals 4. And so we could say that every point on the graph really is given by some x and then some f of x, and that's the ordered pair that we're going to get there. So in the next video, we'll look at how we determine end behavior of graphs. Cheers.